I ended by saying that I would like to explain how this nu is related to the nu from the configuration model. And the way how to see that they're related is to recall, that's something that I discussed on Monday. If you look at the proportion of vertices in my graph that have a degree equal to k, then this actually is converging to this Poisson value, Poisson probability with a random parameter. So you could also say that this is the same thing as the probability that a Poisson random variable with parameter w is equal to k. Okay? So this is my degree distribution. And also I argued that in the generalized random graph, if I condition on the degree distribution, then it ought to be the same as the configuration model condition on simplicity. Okay, so let's take these two for granted. Then it should be the case that these results are very alike when I were to take this as the degree distribution. So if I look at the previous slide, I actually got that nu was equal to the expected value of d times d minus 1 divided by the expectation of d. Now the expectation of d should now thus be the same as the expectation of this Poisson random variable with a random parameter. But then I can condition on the parameter, and the expectation of the Poisson will be its parameter. So this is nothing but the expectation of w. And in a similar way, we know that for Poisson random variables, if I look at factorial moments that are going down, like here, then that is going to be a power of the parameter. So if I compute this thing conditioning on w, I'm going to get w squared. So then this will be the expectation of w squared. This is going to be the expectation of w. Which is precisely what it is here. Okay? So these results are very alike. There are things that are quite different because here you cannot have a giant component that can be of size n, but apart from that the results are very, very universal. So you can really think of this result as saying that the giant component in the generalized random graph converges to a limit, and you would get precisely the same limit if you would start with a configuration model with that Poisson W degree distribution asymptotically. All right. So this somehow describes that the configuration model and the generalized random graph are very closely related. So in some of the things that will follow, I will actually focus a little bit more on the configuration model, and then I'll leave it to you to figure out that then in fact many of the results are also going to be true for the generalized random graph. I will still state some of them, but not always. So what I would like to discuss next is the small world phenomenon. And remember that the small world phenomenon was saying that in a very large network, how the number of pairs, or the proportion of pairs that are if I look at the graph distance between those, then that's actually relatively small. So in many samples that are of size 100,000, a few million, sometimes even a few hundreds of million, you see that these graph distances are typically of the order 5, 6, 7, 8, 9, 10, or 11, or something like that. So they're relatively small. So how do we model that? Well, if I look at the probability mass function of a uniform pair of vertices, I can think of that as somehow taking the expectation with respect to a uniform pair. So what I would like to do is now study how that as a random variable behaves. So bear in mind, this is even a random variable in a deterministic graph. So I'm going to take Hn, which is the graph distance, which I'll denote by this, in the graph of choice, whatever it is, between a vertex 1 and a vertex 2, and vertex 1 and vertex 2, are chosen in my vertex space. It's the only thing that I'll assume, namely that the vertex set has size n, uniformly at random. Okay? So that's my random variable. So if I do this in a real-world network, and I plot its probability distribution, then I get precisely the plots that I was showing on Monday. This histogram of distances 5, 6, 7, 8, etc. Because I was renormalizing those. Now there's a little tweak here, because we've already seen the phase transition for the giant component. So it could actually be that if I take these two vertices, that they're not connected, even when I have a giant component. Well, then the graph distance is infinity. That's not so interesting. You can compute exactly what that probability is. One in the giant, the other not, or both not in the giant. Okay? So that's 1 minus zeta squared. So now I'm done with it, and I'm just going to assume that they're both in the giant. If they're both in the same connected component but not in the giant, then this is very much related to the size of the second largest component, and typically this is very small. So conditioning on V1 and V2 being connected is basically the same thing as saying that they're both in the giant component, when you're in a situation that there is a giant component. Okay, so now what I would like to study is this random variable, and in particular I would like to investigate how this behaves. If I know the law of this object, when I average out over V1 and V2, I know everything about the distances in the graph. For example, the supremum of the support of this thing is going to be the diameter. Okay? Well, I'll just look at the typical behavior of this thing. So this is sometimes called typical distances, or average distances, rather than maximal distances, which would correspond to a diameter. Yeah? And now what I'll do is I will take G to be a random graph, and then investigate how this random variable behaves. Okay? And what we see is that there's two different behaviors, depending precisely on the power law of the degree distribution. If the power law is sufficiently large, that means here larger than 3, finite second moment, then it turns out that these graph distances behave logarithmically. Now a logarithm of n is actually not a very large number, if n is 100,000 or 1,000,000 or so. So you could interpret this as saying a sort of a quantified statement of the small world phenomenon. Okay? I'm assuming that there is a giant component. We've just seen that that is the same thing as saying that this nu is larger than 1. And then I condition these two vertices to be in the giant component, and I just count the length of the shortest path between them. That's what I'm doing. That's what this is. And this says that if I look at Hn and divide by this particular factor, and again the same nu appears, we've now seen it 3 times. First of all, it determines the giant component, previous theorems. It also determines the probability of simplicity. It was the same nu that appeared. And now it also determines the graph distances in this way. Right? So this is a pretty important parameter. I'll explain later on where it comes from and why it's so important. Okay? So this says that Hn divided by log nu of n converges in probability to 1. So Hn is roughly logarithmic with base nu. Okay? And there's a stronger result that says that if I don't look at the ratio, but I look at the difference between the two, Hn minus log nu of n, and that's actually a tight sequence of random variables. Now, if you're a probabilist and you prove that some random variable is tight, then we all sort of think, you know, actually if it's tight, then it will actually converge. Now, this is an example where it doesn't converge. It's not that we cannot prove that it converges. We can prove that it doesn't converge. That's a stronger statement. And that's related to the integer behavior. Of course, this distance is an integer number, whereas this is not necessarily an integer. So if you subtract, well, you know, you're going to be hopping around the integers all the time. And you think you may solve that by taking the ceil or the floor of this number. That doesn't quite solve it. Because there's still the parameter as to how close you are to an integer, this logarithm, that will appear in the limiting distribution. So if you look along sequences for which the deviation of log nu of n to an integer is fixed, these are exponentially growing sequences, then you will actually have convergence along those subsequences. Okay? A very detailed statement. The second statement looks at what happens when tau is in between 2 and 3. So think about perfect power laws, the degrees being IID, with a power law exponent that is tau, and tau is in between 2 and 3, infinite variance. Then it turns out that Hn is a lot smaller. So this is sometimes called a small world, logarithmic distances, just like in the small world model. Here it's called an ultra small world. It's a double logarithm. So Hn divided by a double log converges to a constant, and in fact doesn't depend on anything of the degree distribution except for the power law exponent. It's the only thing that it depends on. And again, there is this statement that if you look at the subtraction of the two terms, Hn minus this times log n, that's again a tight sequence of random variables that again doesn't converge, provably. And also there's a lot of very precise and sharp knowledge here. What happens if you, for example, cut the degree distribution at a certain value? So if I take an IID sequence, the largest value is going to be n to the power 1 over tau minus 1. Classical extreme value theory. Right? So let me write that down. So if I have d1 up to dn such that the probability that di is greater than k behaves like a constant over k to the power tau minus 1, that's how I define my power law exponent. And if you look at d max, that's the maximum value. These are IID. And this actually is going to be n to the power 1 over tau minus 1 times some limiting random variable. Let's call that m. In distribution, if I multiply this to the other side, it will actually converge to this limiting m. So that means that the largest degree that I will see is n to the power 1 over tau minus 1. If tau is in between 2 and 3, that exponent is pretty large. It's larger than a half. And it can take any value all the way up to 1. It will always be strictly smaller than 1, but it can be all the way up to 1. Okay? Now you could wonder what would happen if you would not look at this, but look at an IID sequence where you take di, let's say di of n, because now it is going to depend on n, is di conditionally on di being smaller than something. Let's call it n to the power beta n. Where beta n could converge to 0, or it could be 1 over 100, smaller than this value, or something like that. And we know that actually the graph distances are affected by this change. And we will see later on why that is. Somehow in very loose interpretation, what happens is that from a certain time moment on, the shortest path will go through vertices that have an ever-increasing degree. And actually the degree will go up by powers. So I have a degree, and then the next vertex that I'll take along my shortest path will be that previous degree to a power larger than 1, and then to the same power again. So you get these powers, and that actually goes pretty quickly, which is why this is so small. And you do that all the way up to the moment that you're in one of the hubs, one of the very large degree vertices. And then from that hub, you go down to the other side. And this was precisely the picture that I was describing on Monday, where, you know, if you want to understand 6 degrees of separation, you think about a highly connected person that you know, maybe the director of the high school or the university or somebody highly placed, and then that person thinks of the most highly placed person that that person knows, etc., etc. You take a few steps and you actually go pretty far. That's actually really what these shortest paths here look like. But then, if you do this restriction, and you're going to be cutting out all the hubs, then you'll have to take a much longer route in order to avoid them. So really, the distances go up rather tremendously. And I will argue these statements. I don't think it will be today, but certainly on Friday, how you can interpret these results and understand why these results are precisely what they are. All right. Now, 6 degrees of separation revisited. Just a plot of the log, which is the one thing that we see here, and the log, that's this one, which is what we see here. And I do this for numbers that are pretty realistic, for, let's say, a population of the world, 10 billion. Okay? Now, from your perspective, you will not be able to see that this is not a constant. Now, if I look here, you can sort of see that it goes up. But even I have to squeeze my eyes. Now here, that's pretty obvious. It will be clear that this goes up. It goes up very slowly, but it does go up. So it's easy to see that the logarithm tends to infinity. Apply it once more, you don't see it anymore. So for all practical purposes, numbers that are of the order of magnitude that we're interested in, we're not going to see that log n tends to infinity. So you should think of this as being 6 degrees of separation. This really is a quantification of that paradigm. It's more of a philosophy than a theorem. But this actually quantifies it in this particular case. Yes, which actually does make perfect sense. Yes. But of course I'm cheating a little bit because there is this funny constant here. Yes. There is a 2 in that constant, and that's precisely the 2 that you're referring to. Yeah. But there's this other funny thing that actually makes it slightly larger. Good point. Okay. Now some more precise results. If you look at this Hn, which we sometimes call the hop count, that's a terminology that comes from electrical engineering, graph distances, typical distances, they tend to be fairly robust, and they tend to be relatively small. Now it could of course be that you have rare parts of your graph that are doing something weird, and that actually give rise to a diameter that's much larger. For example, you could have a very long path of vertices of degree 2 only. That's going to change the diameter rather dramatically. Whereas it doesn't change the graph distances by much because it's very thin in a zoo of many more vertices, so you're not going to notice it. So if you look at the diameter of the configuration model, there is an impressive result by Fernholz and Ramachandran, which actually shows that this diameter is again of the order log n, typically, even when tau is in between 2 and 3. When you have vertices of either degree 1 or degree 2. Okay? And then actually, so for tau in between 2 and 3, nu is infinity, so this is 0, and this is strictly positive. Okay? So the only case that is still remaining to determine what the diameter behaves like is the case where tau is in between 2 and 3. So this is infinity, this is 0. And the minimum degree is equal to 3. And that's really a different case. And there it turns out that also the diameter is doubly logarithmic. So we already recognize this part, just like we recognize this part as being the typical distances. And you add a little bit to that, which is strictly positive. So that means that the diameter acts on the same scale as the typical distances, but the constant is slightly larger. And that's due to somehow a local, unusual situation that makes distances very large. So here, the local, unusual situation is that you're going to have a string that is very thin, that's quite long. And here, the thing that is pretty rare is going to be a tree that has, where every vertex in the tree has degree d min, and it will have this depth log n. So not only do these results say something about the diameter, but it also tells you something about what the local structure looks of vertices that realize the diameter, which is interesting in its own right. Okay, we can do something similar for the generalized random graph. And as I said, the configuration model and the generalized random graph are intimately related to one another. So you're not going to be surprised to see that you actually have precisely the same result here as well as here. So this is another sign that these two models are very intimately connected. Now here you can prove this even through a route that is similar to the route that I was describing before, namely configuration model conditioned on simplicity has the same law as the generalized random graph conditioned on its degrees, and then you analyze that model. Here that doesn't work so well because the probability of simplicity is vanishing. So here you really have to do it again for this particular model. But the methodology is very similar to the methodology for the configuration model. So it's not that you can sort of lift the result directly without doing anything, but you can lift the proof and adapt it to the particular setting. Okay? All right. So before I want to say something about proofs, I would like to describe a similar situation for the preferential attachment model. Now, preferential attachment models have attracted quite a lot of attention, but it's mainly the degree distribution that has been investigated. And I've shown you the proof for sort of the convergence of the empirical degree distribution, which is fairly beautiful. And indeed, the degree distribution is something that you can analyze relatively easily. Another thing that you can analyze relatively easily is how the degrees in the graph, let's say the degree of vertex 1 or the degree of vertex 2, how they increase as time progresses. There's also a nice martingale argument that will tell you how that goes. But if I'm talking about graph distances, I really have to look at long paths inside the graph. And of course, it's a dynamical network, so it's pretty difficult to do that. Somehow the dynamics in the description of the model makes it pretty hard. Because it could be that, you know, if I'm taking a path, some may be along edges that are going in the right direction, let's say from young to old, but some other parts of the path may actually go from old to young. And then it becomes a bit difficult how to analyze those probabilities. So it's actually not an easy problem to study graph distances in the preferential attachment models. But of course, I mean, for physicists, this is no problem whatsoever, because they basically say, you know, all of these models are in the same universality class, and therefore the behavior should be the same. So they even have something which is called the mean field preferential attachment model. And this is the model with delta is equal to 0. And I can write down what it is because it's just one of these Chung-Lu models, or one of the generalized random graphs. You take an independent, you take a graph where the edges are independent, but the edge probability Pij, so this is delta is equal to 0, Pij is equal to 1 over the square root of I times j. So in particular, this is of product structure. So this is one of these, it's a Chung-Lu model, basically. It's not quite a generalized random graph, then you would have slightly different edge probabilities, but it's basically that. And often in physics, these models are used exchangeably, but they're really different. And I will argue why they're really different. Somehow the time dynamics makes it much harder, and also makes it really different. Yet, somehow this is, the suggestion of universality is basically saying that, you know, if I were to pick a preferential attachment model, I know exactly what its degree distribution is. I could use that degree distribution inside a configuration model, and then the prediction of the physicist could be translated to saying they should have similar graph distances. Maybe not an unreasonable statement. If it would be very far from the truth, we would be in trouble, because if we're using the preferential attachment model and the configuration model to model the same graph with the same tau, which one are we supposed to believe? Okay? So that's basically the problem here. So this is sort of a general philosophy, and I would say that sort of in general this question is wide open. We don't really know this, even though there are some results that are hinting towards the statement that this is true, and some very sharp results that are saying that it is true. So let me try to describe that a little bit. And as I said, preferential attachment models are much harder because they have time dynamics. So I cannot somehow, in the configuration model, what you could do is you could take a vertex and you can explore its neighborhood. That doesn't work so well in a preferential attachment model, because if I take a vertex uniformly at random, like the source of my of the graph distance, I have these two vertices chosen uniformly at random, I'm going to inspect their neighborhoods. Well, how old are they? And what are they connected to? And some of their sort of immediate neighbors are going to be corresponding to the M edges that he himself pointed out, but there may also be some younger vertices that have pointed it towards it. So that really makes it much harder. Explorations are much harder. Yes? think I'm the right person to ask. But, okay, so how would you do this? Unless you have a very fast computer. But, you know, log n, I mean, you're seeing it, right? I mean, you would really have to go to several orders of magnitude larger. I mean, it's not 10 to the power 10, but maybe 10 to the power 10 to the power 10. Can you still do that? Yes, but if there's a very small constant in front of the log, it might already be very difficult, right? So these are finite size effects, as physicists call them. But indeed, you're right. This is very difficult. In fact, if you want to, on the basis of a simulation, determine whether the growth is log n or it remains a constant, I think you'll be hard-pressed. You'll not be able to do that. Yeah, very good point. All right, let alone seeing that a tower function, or the inverse of a tower function, tends to infinity. That's just completely impossible. Log is already very bad. Okay, so I mean, in the previous models, I was starting out by proving, you know, there is a giant component under certain conditions. It's a setting in which there is a giant component that is relevant for us. That's what we would like to investigate. So connectivity in the preferential attachment model is a bit more tricky, but in a certain sense, it's also much easier. So if I start with a model where I always connect up to vertices that are younger, and if I start with a connected graph, then the graph will be connected by default. Now there are also models in which you allow for self-loops, and then you might actually generate new connected component as time progresses. But it's not very difficult to show that even in that model, the graph is going to be connected with probability tending to 1 almost surely as time is very big. So the connectivity issue is not that hard for preferential attachment. And really when m is greater than or equal to 2. Okay? So you should bear in mind that m is greater than or equal to 2 is somehow very similar to the minimum degree in your configuration model being at least 3. In the configuration model, when you connect to a vertex, you lose one of its half-edges. So you still have the degree minus 1 left over. So while you're exploring, these vertices in the intermediate exploration are going to have forward degree, which is the degree minus 1. Whereas in the preferential attachment model, if I come into a vertex from another vertex, it's still going to have degree m, because it still has its own edges to give. So m here and d min minus 1 should be similar. So that's connectivity. Then about distances. Well, the very first model for which distances were analyzed was the model that Albert and Barabasi were proposing, where there's no delta. Now that's a bit tricky because I was giving you results for when you have a finite second moment and when you have an infinite second moment with a tau which is in between 2 and 3. This is tau is 3. Precisely, right? Because tau was 3 plus delta over m, delta is 0, tau is precisely 3. So for a very long time, we had this situation that there was one case for preferential attachment model that we understood. There were lots of cases for configuration model that we understood, but this one case that we understood for the preferential attachment model, we didn't understand for the configuration model. By now, that has been cleared up a little bit. I certainly do want to mention the result, which is by Belo Bolobash and Oliver Reardon, and they show that the diameter as well as the typical distances grow like log n over log n. Actually, the same thing is true for the configuration model as well as for the generalized random graph, when tau is exactly equal to 3. When there are small modifications, then these graph distances change. So that's this very first case. But somehow it doesn't allow us very easily to compare to the previous results for the configuration nor the generalized random graph. Now then there's a second case, m greater than or equal to 2, finite variance, so delta strictly positive. Well, then we don't know very much. The only thing we know is that the diameter is in between a very large constant and a very small constant times log n, and also the typical distances are in between a large constant times log n and a small constant times log n. That's the best thing we know. We don't know what this constant is, or that there is a constant. I do believe, I think this is a pretty interesting open problem, It may be hard. Certainly at that time we did not have the tools to prove this. I believe that if delta is positive, which is the same thing as saying that tau is strictly larger than 3, which is the same thing as saying that you have finite variance, then if I look at the diameter of the preferential attachment model at time n, and I divide through by log n, this is going to converge to a 1 constant, but I have no idea what it is. And if I look at the graph distances, divide through by log n, then this will converge in probability to another constant. And again, I don't know what it is. Nice open problem. But going back to the analogy between the configuration model and preferential attachment models, this certainly is a good sign. Both the diameter as well as the typical distances are of the same order of magnitude as what they are for the configuration model as well as for the generalized random graph. So this is certainly not contradicting the universality claim, even though it's not proving it as sharply as you might want to. Yes? Yes, that's a Chunglu, or the generalized random graph, yeah. Oh, this? For when tau is greater than 3? Oh, I didn't say that. Similar extensions for diameter as for CM. Basically, the result still applies. But here, bear in mind, there's one difference. So the case where tau was in between 2 and 3, and the minimum degree was at least 3, was special for the configuration model. That cannot occur here. Because in generalized random graphs, you will always have vertices of degree 0, you will always have vertices of degree 1, and you will always have the vertices of degree 2. Right? So that predicts that the diameter will always be logarithmic. If only because there might be a very long path starting with a vertex of degree 1, going through vertices of degree 2 along the way. So it will always be logarithmic. There's no phase where the diameter is doubly logarithmic. Does that answer your question? Yes. Yes. Yeah. Right. Well, not the generalized random graph. 3. Let me explain. So for the generalized random graph, I guess you would have to take 1 over the square root of ij divided by 1 plus the square root of ij. Which is almost, am I doing this right? Yes, which is almost the same, because typically this is going to be very small. Right? So let's do it for this one. So on Monday I explained how you can relate the weights to the power law. And the way how that goes is that the weight is some constant, which is not very relevant, I'll just take it to be 1, n divided by I raised to the power 1 over tau minus 1. That's how it goes. And that's very much related to this arithmetic that I was doing for the maximum. Here you see that the maximum weight is n to the power 1 over tau minus 1. Just like the maximum degree for the configuration model. And the maximum weight here is going to correspond to the vertex of maximum degree. So it's really in line. Okay? So when tau is 3, this is a square root. Right? So I can think of Pij as being, now I have to think, Wi Wj divided by n. Yeah, divided by n. That is the same thing. With this choice of the Wi Wj's. So this is closely related to a generalized random graph. You always have this difficulty of, I mean, how are you choosing your edge probabilities precisely? Are you dividing here through by the sum of the weights? Well, they're the same order of magnitude. Does that answer your question? Very good. So this is really the model for tau is equal to 3, apart from appropriate constants or whatever. All right. Yes. Now the situation, this is weird, because typically the situation where tau is in between 2 and 3 is harder than the situation where you have finite variance. Because it's much more difficult to do computations. Because you're in this heavy-tailed phenomena, lots of fluctuations, very high degrees. Yet here in the preferential attachment model we can actually do more than for this case. Because in particular we can figure out that again these typical distances are of size log n when delta is strictly negative, which is the same thing as saying that tau is in between 2 and 3. But here we can identify the constant precisely. And this constant looks a lot like the constant we had before. Let me flash that back to you. 2 over the absolute value of log tau minus 2. 4 divided by the absolute value of log tau minus 2. So they're identical in terms of the constant, except there's an extra factor 2, which is weird. And I will explain when I go through the proof, I will discuss the proof of the configuration model in some detail, and I will explain where the extra factor 2 comes from. So basically it boils down to the following. I was describing that short paths in this setting are formed by taking a vertex of large degree and going in one step to a vertex that has a much larger degree. In fact, a power larger than 1 of the degree of the original vertex that you go to. Now in the preferential attachment model, it doesn't work that way. If I have a vertex of very high degree, it's going to be a relatively old vertex. Now of course this could be immediately connected to a much older vertex, in which case it would have much higher degree, but this is relatively unlikely. So instead what happens is that there's going to be a third vertex that is actually going to connect this vertex to a much older vertex in this setting. So again, vertices of high degree are connected to vertices of higher degree, a power larger than 1 of their current degree, but you have these intermediate vertices, we call them interconnectors in between them. So rather than them being directly connected, they're connected by 2 hop paths, which makes the distances twice as large. That's it. Okay? So I'll say a little bit more on Friday about the precise way how these proofs go. And it turns out that we can also prove the asymptotics for the diameter. That's actually harder, quite a bit harder. And it's very recent. It's a paper with Francesco Caravenna, a PhD student of mine, Alessandro Garavaglia, and it's just been accepted for RSA. But the funny thing is that the result is identical to the result for the configuration model. Here we see, this is the constant for the typical distances, and then this is 2 divided by somehow the minimum forward degree. Now we look at this. This is the constant for the typical distances, 2 divided by the log of the forward degree. So very closely related. And also the proof is very similar in the sense that what you would like to analyze is somehow the vertices that are most likely to form the diameter. And these are vertices whose nearest neighbor tree is what we call minimally connected. It really has the minimum number of possible neighbors. Now in a configuration model that would be the case when the root has degree d min, and all of the further children also have degree d min, but then it means that they have forward degree d min minus 1. The preferential attachment model is a little different. The vertex that you start with has degree m, and then it connects to another vertex, one of its m edges, but that vertex still has degree m, its own edges that it has given when it came in. So that means that the intermediate vertices all have degree m plus 1. So there's a plus 1 minus 1 effect here. So if you just literally replace the m here by d min minus 1, that added effect is the same. And we actually can prove that these local neighborhoods really are the ones that are going to maximize the diameter. All right. So I want to say something about the proofs. I will not be able to do the entire proofs, but I want to describe some of the philosophy behind it. Now, many of you know that if we're dealing with random graphs, often we can compare them to branching processes. And there's a relatively recent technique that has proved to be very powerful, and that's the technique of local weak convergence. And I will say something about that a little bit later on, which is probably going to be on Friday. But here's the basic philosophy. So suppose I take one of these uniform vertices here. Here I call them V1, there I call it U1. Okay, it's a uniform vertex. If I do this in the configuration model, I actually know precisely what its degree is, because that's this dn random variable that has this distribution function fn, of which we were assuming that it's converging in distribution. Because the degree distribution converges, that was the same thing as saying that if I pick a vertex uniformly at random, then it's going to have a random degree, but that as a random variable converges in distribution. So, you know, if I pick a vertex uniformly at random, that's precisely what I'm doing. So I know precisely what the probability is that I'm going to see 4 neighbors, 5 neighbors, 6 neighbors, or whatever. That probability is roughly going to be the probability that my asymptotic degree distribution takes on the value that you're interested in. So that's a relatively easy step here in this analysis. It becomes a little bit more difficult if you want to talk about the neighbors of the neighbors. So I have my root, it has 5 children, then how many further neighbors are each of these 5 individuals going to have? Well, that's very nicely described by how by the configuration model dynamics. Because I explained on Monday that you can choose in which order you want to pair the half-edges. So take any half-edge that is incident to your root, and just think about pairing that one first. What is the probability that's going to be connected to a vertex of degree 25? And thus having 24 more children. Well, it has 25 half-edges. I'm connecting uniformly at random, so the probability is 25 divided by the total number of half-edges. Well, -1, but I'm ignoring the -1. Right? And that's true for every such vertices. So I'm going to get, well, the value that I'm interested in for the forward degree, +1, divided by the total number of half-edges that we have. That's uniform connection. But of course, there may be many vertices that have that degree. It's precisely this. Okay? Now this actually is it's n times the average degree. The average degree converges to this. If I divide this through by n, which I can get by pulling the n out of here, then I just get the proportion of vertices with degree k+1. But that converges to the probability that d is k+1. Because I'm assuming that my degree distribution converges. And then I still keep this k+1 here that is just there because, you know, a vertex with more half-edges is more likely to be connected to. And that gives me what this limiting forward degree of a neighbor of the root is. So now I know what the degree distribution of the root is, and I know what the forward degree distribution of any of its neighbors is. But this actually is a nicely defined random variable. It's going to be finite with probability 1. So that actually means that I'm not eating away too many half-edges after this pairing. So if I pair the next one, remember I had this root of degree 5, I want to connect up all these 5 half-edges. I've now paired the first one. It eats up a certain number of half-edges. But that's, you know, a small number. It means that sort of in the whole z of n, in the whole c of n half-edges that I had, a few are going to be removed. But the probability that I'm going to create a clash with that, that's going to be vanishing. So basically, if I pair the second half-edge, it's like I haven't done anything in the first half-edge. Okay? So it's going to be pairing to a vertex completely independently of the first one. And again, with that distribution. So that means that sort of asymptotically, if n is very large, if I start exploring around a uniform vertex, what I will see is roughly a tree for which the root has degree distribution d, and then this has forward degree distribution that is given by this law, and that's the same thing as the size bias distribution -1. So this is size biasing if it would not have the +1, and the +1 creates for an extra -1. That's true for this one, and then this one has that's true for this one, that's true for this one, true for this one, true for this one, and they're all independent. But then I can iterate, because this again corresponds to half edges. So if I do it here, I'm again going to get the same random variable, IID copy. This is a branching process. I have a root with a certain degree, and then all the other individuals in my tree, if n tends to infinity, are going to have IID copies of another distribution, and this other distribution is precisely this. Okay? Exercise, because I'm done. Show that nu is the expectation of d star minus 1. And then you understand why nu larger than 1 is relevant. We know that branching processes have a positive probability of surviving when their expected offspring is larger than 1. Now we were always saying that this nu had to be larger than 1 in order to have a giant component. Well, if nu is larger than 1, you know that with positive probability, this branching process here will survive forever. Now, of course, at a certain moment, I cannot make this coupling between the branching process and the graph exploration true. That will only be valid up to a certain point, because this branching process can actually be truly infinity. But if I do a graph exploration, I can never get more than n vertices. So there's bound to be some difference occurring somewhere. At least for a small number of steps, you can do this. So what I'll do on Friday is I'll make this a bit more precise. And the way to make that more precise is all about the notion of what is called local weak convergence. That has proved to be a very powerful tool. And it's very powerful in, sort of at least intuitively understanding, let's say, the law of the giant component, the law of the distances, etc., etc. So that's for Friday. Thank you.